Notes on confidence intervals for the difference of two means. I'm going to go ahead and highlight as I talk. You may or may not want to follow along. Review. A confidence interval gives a range of plausible values for a population parameter, in this case the difference of two means. Remember, what we used to do was we take a sample to estimate the actual average in the population. And then we would create a confidence interval because we know that estimate is probably wrong based on sampling variability. And so we'd create a confidence interval around it to say, we're pretty confident that the actual value falls between this lower bound and this upper bound. Well, now we're going to do the same thing, but with the true difference of the means. So we're going to subtract the two averages first. Here's an example. To test if a new fertilizer is effective, two similar tomato plants, they need to be similar to minimize confounding variables. They were randomly assigned to be planted in either regular soil or soil with fertilizer. So we have the regular soil or soil with fertilizer. After 3 months, the total weight of the tomatoes from each plant was measured. These figures in pounds are below. So here we have the weights of the tomatoes grown in the regular soil and the weights of the tomatoes grown in the fertilizer soil. We are going to construct and interpret a 95% confidence interval for the difference in mean production for the two conditions. And then we're going to use that to answer the question, does the interval give evidence that soil with fertilizer is more effective than regular soil for growing tomato plants? So we're going to start by finding out the average and the standard deviation for our samples. So we're going to put this data in list 1 and this data in list 2. You can see that I have list 1 data and list 2 data. So this is regular tomato plants and fertilizer tomato plants. And we're going to go ahead into stats, tests, and we are going to do a 2 sample T interval, because we have to do T because we don't know the true population standard deviation, just our sample standard deviations. Hit enter. We don't know the statistics, but we did have the data and we put it in list 1 and list 2. And we want a 95% confidence interval. We never want to pool, and we're going to ask it to calculate. And if we can do that, right there is my confidence interval with the degree of freedom of 17.4. Now this is the crazy looking degrees of freedom we talked about earlier in class that we use for the 2 sample hypothesis test. You could also use the more conservative one, and we'll talk about that in a minute. Here was the average weight for the regular soil and the average rate of the tomatoes in the fertilizer soil. Right now it appears that the fertilizer made bigger tomatoes. Okay. I went ahead and wrote in the mean and the standard deviation that we got from our calculator. And we're going to go ahead and do the 4 steps. We've basically already done everything, but we're going to write out our work now. So step number 1, we are trying to estimate the true difference in the mean weight of tomatoes grown in regular soil and mean weight of tomatoes grown in fertilized soil. Our best guess is negative 2.6, because if we subtract the 7.3, excuse me, that should go right there, the 7.3, and take away from it the 9.9, we should get this difference. So that's our best guess. But because of randomization variability, it's probably incorrect. Instead, we will calculate a 95% 2 sample T interval, which we already did. However, we did that so we could get all of our information down. We still have to check to make sure it was okay to do it. Were the treatments randomly assigned? Yes, so that is taken care of. If not, we would have to proceed with caution. And we do that to make sure that the plants and the soils are independent. We also need the populations to be approximately normal, and our N is only 10 for both of these. So since it's not greater than 30, we have to go ahead and do an NPP. Both of these are also approximately normal, so we can assume the populations are both approximately normal, which is nice. Now that we've checked our conditions, we'll go ahead and do our confidence interval. Notice this is the confidence interval, you may not have written down, that I got from the calculator with a degree of freedom of 17.43 and a t-value of 2.106. And I don't actually know if that t-value was in the calculator, I just checked, and the t-value right here, 2.106, was not from the calculator, but I found it doing inverse t using 0.975, because that matches the 95% confidence interval, and the degrees of freedom of 17.4. And so this was the calculator confidence interval, a difference of negative 4.154 pounds to negative 1.046 pounds. However, if you look at our step number 3, it's slightly different. We still did the same thing. It's the difference of the averages plus or minus the critical value times the standard deviation. But this t right here came from the conservative degrees of freedom, which is just the smallest sample size. In this case, they're both 10, minus 1, which is 9, which would give you a slightly different t-value, 2.262 versus 2.106. And then, of course, you could do the math, and this would be the conservative confidence interval. Notice they're not that far off. Negative 4.27 versus negative 4.15, negative 0.93 versus negative 1.046. You should know how to do it by hand, but I'm okay if you always do it in the calculator as long as you could show the work by hand in order to answer questions maybe on the multiple choice section. So bottom line, really we did it all up here. Put it in list 1 and list 2, run a 2-sample t-interval. It'll pop out your statistics for both samples as well as your interval, which was right here, which was better. And now all we have to do is look at our last step. I am 95% confident that the interval from, and you can use this one or this one, captures the true difference in mean weight for tomatoes grown in regular soil and for tomatoes grown in fertilized soil. Here's the key part that answers our question. Since the interval of the plausible values is entirely below 0, and 0 means no difference, we can conclude that the mean weight is greater for fertilized plants. Because if the mean weight is greater, if you do regular plants minus fertilized plants, if this one's bigger, then it's always going to be a negative value. And notice that our confidence intervals are solely negative. So we can kind of just assume that the fertilizer plants are always better. Because what we've done is we've guessed the average difference, and our guess, which we're 95% confidence about, is negative, no matter what. Now, I want to compare that to the hypothesis test. If we wanted to do a hypothesis test for this, we'd say, well, our null hypothesis is that the actual weight of the regular plants minus the actual weight of the fertilized plants is 0. There's no difference on the soil treatment. And our alternate hypothesis is that, and I have to change this real quick. I paused and erased. I actually had X bar right here, which is horrible because those are the statistics and we're making hypotheses about the actual values. And we're saying that we think this one is bigger, that the plants grow bigger, so that if you subtract the 2 in this order, it'll be less than 0. So we'd go ahead and run a 2-sample t-test. We get a t-value of negative 3.52. Be very careful, this is not the same as the critical t-value up here. It's not the same. This is the t-value for our specific difference. And we have degrees of freedom of 17.4, so it's the same. And we get a p-value of 0.00126, which means the probability of getting a difference of what we got here, which was negative 2.6, the probability of getting a difference this extreme or more extreme, if they're actually the same as far as the fertilizers make the same size tomatoes, is almost 0%. So we could go ahead and reject our null hypothesis that they're the same and conclude that the mean weight is greater for fertilized plants. We make the same conclusion. So go ahead and read the chapter and see if you can see how those two link. And then I even wrote down here how you could find this. It is just a t-CDF, but again, you can use a 2-sample t-test and that could do it for you. This is just linking to what we did in class. You've now kind of maybe can see that a confidence interval can answer the same question that a hypothesis test can. They just go about it in different ways. All right, let's try one more example. A recent study investigated the effects of fast food consumption on other dietary variables. For example, 663 teens who reported that they did not eat fast food, so they tend to kind of eat healthy, during a typical day had a mean caloric intake of 2,258 with a standard deviation of 1591. While they took a sample of 413 teens, notice that the ends aren't the same, and that's okay. And those teens reported that they ate fast food on a typical day, and they had a mean caloric intake of 2637 with a standard deviation of 1138. We're going to construct and interpret a 99% confidence interval for the true difference in the mean caloric intake for these two types of teens. So I went ahead and defined my variable as H, being for the non-fast food eaters, H for healthy, and F being for the fast food eaters, obviously F for fast food. You can kind of streamline step one, but you have to make sure you define H and F. You have to make sure you define the difference. Basically, everything I have in step one you need to say, just not in so many words. So I'm going to go ahead and do my full step one and read it for you. We are trying to estimate the true difference in the mean caloric intake of fast food eaters and the mean caloric intake of non-fast food eaters. So here's a definition you have to define if you didn't say it in a sentence. Our best guess is 379 if you subtracted the 2, but because of randomization variability is probably incorrect. Instead, I will calculate a 99% confidence interval for the true mean difference and mean caloric difference. Okay, now we have to test our conditions first. We would like the samples to be randomly selected. Now, they were not stated, but hopefully it was implied because some pediatric, looks like doctors did this, so hopefully they would know to do it random. So we're going to say, hopefully it was implied, but let's proceed with caution. And then we need it to be approximately normal. Well, our n's were definitely greater than 30, so we didn't need to do an NPP. Now that we've talked about our conditions, we're going to go ahead and do it. At this point, honestly, you can just go to a 2-sample t-interval, plug in your statistics, and hit enter. And you would get this confidence interval. It will give you degrees of freedom of 1038.16. You could use that in inverse t to get a t-value for right here. You can show all of this work, and you do need to understand this work and be able to use the formulas for the multiple choice section, but you don't need to write it down on the free response, and I don't care if I see it on the homework as long as you show everything else and label everything else. So what we've gotten is that the difference seems to be anywhere between 169.1 calories and 588.9 calories. Okay, and that is a positive amount. And since we did the fast food people minus the healthy food people, it looks like the fast food people are eating more calories. So we're saying I am 99% confident that the interval from 169.1 to 588.9 captures the true mean difference of fast food eater calories minus healthy food eater calories. And we might want to use this to answer the question, okay, if the question was asked, which it wasn't in this example, do we think fast food eaters are eating more calories? In this case, I do, because their difference, no matter what, is greater than 0. Okay, so here's your next homework. You might want to start it before class next time, but you don't have to, as it will be due Friday, April 1st for both classes.